just, you know, it's fun shit in the last week, so I've been well on this one. So like, I'm gonna create back up this. But I don't have astro in like 2 weeks. Yeah.
Okay, today's the advent of the Irish way to look at the Trebuchet, and they should know they built them long ago. But what we'll mainly do today is go ahead and show how all of our Lagrangian Trebuchet stuff relates to the Hamilton one. But before we do that, let's just go through the derivation of the Hamiltonian form and equations. And then the Poincare invariant relations. And then finally, we're going to go ahead and write the contravariant metric tensor form for that Hamiltonian. Then we'll discover that the algebra is formidable, much more so than the Lagrangian. So we're going to take advantage of what the Hamiltonian offers us, and that's some symmetry analysis. That is, you can make a momentum that's conserved under certain conditions that are appropriate, but you, in this case, can always make something that has energy conservation. That is, the Hamiltonian will be constant if it is not an explicit function of time, which it won't be here. And then we're going to go through some algebra of that. And at that point, I will stop and we'll just imagine a trebuchet that is out in space. We're going to free space it, give it some momentum, and see how it throws something, given that. First will be an algebraic approach, and then a fairly direct approach in which we can compare. Remember, our superball has some peculiar properties, and they're still on the blackboard over there, so we're going to make a comparison between that. And then finally, I want to come and just get physical with this stuff. Heck with Hamiltonians, heck with Lagrangians. Let's just go back to basic stuff and talk about sports kinematics and just simple ways to look at that. More simple models than what we've been dealing with here. So, there's the pictures we've already looked at. I would add one extra one to this. And we're not too far away from St. Louis, and just to the east of St. Louis is a town called Cahokia, and it has one of the few really comprehensive Native American Indian settlements, complete with very huge pyramid-like earthen structures, and then a complete museum now. It's now a national monument or something like that. And it's worth seeing. It's really quite humbling to know that in the 12th century these people had an amazing civilization. And it included, this is their hunting tool, and I don't know whether it was used as a weapon or not. We won't get into that, but it could well be. In any case, we're going to start with a Lagrangian, and we've essentially already done this derivation of the Hamiltonian from what we know about the Lagrangian and the zeroth equations of both the Lagrangian and the Hamiltonian. So that's where we start here with a differential of the Lagrangian and a linear differential it is as a function of the coordinates, a good old beam theta here for the whole monstrous beam and large mass m, and then the throwing angle, all measured relative to the stars, as it were, relative to the lab frame. All these angles are angles that are not in a moving coordinates. And then there are time derivatives. And then perhaps, let's just start off here, assuming in fact we are going to mess with this thing as an explicit function of time. And so we have here that extra term to deal with in general. So, guess that's a thing. I'll get it going on this screen as well. The first derivative, time derivative, the total time derivative of the Lagrangian is just gotten here by going ahead and putting a dt in the denominator of all of the differentials. So this is a velocity chain instead of a first differential chain. Again, something you've seen before when we were just starting with a single polar coordinate particle. And then we're going to use Lagrange's equations. Okay, first of all, the partial derivative with respect to the coordinates. Well, that is the momentum dot. That's the second Lagrange equation at work there. Okay, replacing each of those with a p dot for both theta, the beam, and the projectile angle, phi. And then this is the definition of momentum in a Lagrangian scheme. The dot now sits in the denominator of the partial derivative and gives you the momentum. So again, beam momentum and this is angular momentum, projectile angular momentum. So that is now going to go together into a total time derivative of our Poincare action combination that gives us these four terms here when you apply that first derivative operator to these. So that includes the acceleration of the projectile and the beam, as well as the velocities of those two things. So that's pretty much it. You now have, just by rearranging this a little bit, an equation that tells you, and takes this partial derivative guy and puts it on the other side of the equation, leaving this thing and the L, bring that inside the derivative here, now with a minus sign, and you recognize Poincare's expression for the Hamiltonian. So basically it's saying the time derivative of this thing, and that's the Irish thing, that's the H, that would actually be 0 in the case that I don't have any explicit time dependence on my Lagrangian or Hamiltonian. So that's the dH dt, the actual total time derivative, taking account of everything that can move. And then this is just a partial derivative, just taking account of whatever artificial messing around, knob twirling that something is happening to this device. Today we're not going to have any knob twirling, so this will be 0 there. Nevertheless, this is a general expression, and this is the Legendre transformation from the Lagrangian to the Hamiltonian. These are all things that we've covered. If you don't remember that, this is the chance to go back and just look at the simple polar coordinate stuff with regard to this. So let's just go ahead and list all of the results in a form that is on the wall over there. And the trouble is that this is going to be very close to the bottom of the screen. That's where we're going to fill here. So the very first thing that I notice is that the partial derivative of this Hamiltonian with respect to theta, okay, what I'm talking about here is actually minus the partial derivative of L with respect to theta. So what I'm doing here is pulling out term by term the results that I would get here just from the basic algebra that we're doing here. Now, the idea is that the partial derivative of this thing right here, the thing we're calling H, this is the whole H right here, and this is just its first part. The partial derivative of that with respect to p theta, the only thing I see there is the theta dot. Okay, well, there is a partial derivative of L to be taken, but remember, L, the zeroth equation, the partial derivative of L with respect to momentum is not an explicit function of momentum. We spent a lot of time worrying about that little detail. So I've crossed that out. This is the Hamilton's first equation, the gradient with respect to P of a particular variable, in this case the beam angle, is theta dot. So that's first Hamilton equation right there. Then let's see if there's anything else here. Partial derivative of the Hamiltonian with respect to theta. The only thing that's left in there is the L. Neither of these things, the velocities or the momentum, are explicit functions of theta. They're independent of that, but this one, of course, has angles theta in it. So I need a minus partial derivative of theta with respect to theta of the L coming there. Okay, so there's a minus P dot theta right there. So really, this is Hamilton's first equation. This is Hamilton's second equation showing up here first. And that's just one variable. We still have one more variable to go. But we go ahead and do the same thing. I differentiate this thing with respect to P, theta dot, then I get the P theta. So I'm getting the first Hamilton equation here, partial derivative of H. Well, this is the zeroth Hamilton. Partial derivative of H with respect to theta dot. That's P theta minus P theta, identically zero. And that's what we want, because this thing is not supposed to be an explicit function of velocity. Either of the velocities, right? And we're just doing theta first here. Okay? Well, doing the rest of them, the same deal. And each time you get a zeroth equation that you just forget about. Okay? Now find me a textbook that mentions the zeroth equation. I haven't seen one. That's a, to me that's a pedagogical flaw of some proportion. All right, let's bring this guy up to the same thing, except it's crawling along the bottom of the screen there. I'm trying to raise that thing. Haven't had much success doing it without killing the top. So, and we're going to have to change some things here to take account of large screen stuff. Okay, so here we go. These are the equations that you see on the wall way over yonder. Got my purple laser here that can light them up. Hamilton's equations are right here. And one of the more miraculous ones, besides the first one, the P gradient, is the velocity. And this is true of all components of velocity and momentum. And then the second one here, the second Hamilton equation, the gradient with respect to the coordinate, that's some kind of force, so it's equal to P dot, but with a minus sign. You see, that's it. These are antisymmetric equations, remember. They have this weird cross-product relation we looked at with respect to the pendulum. And then the weirdest of them all is that the total time derivative of the Hamiltonian, and this is with you messing with it or not, is minus the partial of L with respect to time. That's weird. That's quite weird. We're not going to use it right here, but not right away anyway. Okay. Now, what does it look like when you actually start to write this darn thing out? Because what we're going to have to do here is write our kinetic energy in terms of momentum instead of in terms of velocities. So that's what we're setting up to do here. And one of the things that occurs right away when you do that, you go ahead and put the Poincare form and then subtract the Lagrangian, okay, and since Lagrangian's t minus v, you get a minus t plus v, okay, and then you get this thing here, which is 1/2. This is the Lagrangian's expression for the kinetic energy. There's their potential. and then you get these two products here. Well, they get absorbed into that because they're nothing but one, each one of these terms is nothing but one of those here. Theta dot, phi dot, and theta dot. Well, there are 4 possible quadratic terms in velocity here, and they all melt into 1/2 kinetic energy plus v. Okay? Now, as I say, this is only correct numerically. It is numerically correct to have the sum of the kinetic and the potential instead of the difference is the thing driving here. It is the Hamiltonian in this setting. But this is not right. We have to do something about that. It has to be an explicit function of momentum. So I've got to turn this around. And that's what makes the Hamiltonian more complicated to do, the kind of algebra that we were doing with the Lagrangian. So this is correct formally and numerically. That's a good expression and for this machine of the Hamiltonian.
Okay.
But you see, this sort of thing here with the p's, it's got this denominator. You see, that makes the algebra a lot more complicated. Yeah.
So, well, when you say it's correct numerically versus formally correct,
I mean,
like,
differentially correct.
But so like
Yeah.
from, if I was trying to, I don't know, describe the motion as a function of time and figure out different possibilities that could happen, is there a reason that numerically correct wouldn't be sufficient?
Well, if you could stay away from any derivatives with respect to any coordinates, I would say, yeah, go for it. But how do you do that? Because all the equations are derivatives.
Right. So you wouldn't really be able to solve it at that point because you still have to take, you're solving differential equations to get like position.
You would be using Hamilton's equations, right?
Yeah.
And they're derivative equations. And they do make a Runge-Kutta form. That, I think I pointed that out when we did just a polar coordinate guy, right? Is they're nicely set up to do a Runge-Kutta. But so are the Lagrangians, if you want to be honest about it. It's just that using Mathematica, you can write an expression and have it do that every time step, right? Then the Hamiltonian wins. Okay, as far as machine application. Okay, anything else that we need to do here? Because that's the monster we're going to be dealing with. Well, not for long, as it turns out. I'm going to do this very quickly. I mean, we do have these relationships in velocity and momentum, which are very simple relations, so it's not very hard for me to go ahead and calculate the partial derivatives with respect to the momenta. That's the gradient of momentum that's supposed to be giving me velocities. Okay, that's nice and easy. Okay, but here it starts to get a little bit freaky. Now it's true that when I get the p dots that come out of the minus the partial of h with respect to each of the variables, minus the partial here, which turns out to be that, if you want to follow the connection with Lagrangian. But anyway, this is what I'm coming up with. And as I say, this guy here, a lot messier already than we had. And this one's even worse. So I'm just going to stop here because I see no way through this forest that's worth wasting a class time on. This is showing you that Hamiltonian elegance is not to be found at this point here. It's to be found as you search for various symmetries of the Hamiltonian, and that's what we're going to do fairly quickly here. So, what I'm proposing, and this is a little bit of snatching something that worked out of some searching, but basically I'm going to switch here to some angles. Particularly the phi angle is going to be not measured like this phi angle to a vertical that's fixed to the stars, that is the lamp frame. I'm going to be interested in an angle phi beam, phi relative to the beam. Actually, phi relative to the normal coming out of the axis of the projectile for the beam. So this is a right angle right here, this dotted line with the beam radius. Okay, so that's our new coordinate. And while I'm at it, I'm also going to locate where that is. Where is that perpendicular? That'll be theta b here, measured off of these lab fixed vertical dashed line. It doesn't ever move. So what you're seeing is a relationship here between the difference between phi and theta, and basically it's the sum of theta beam and phi beam. Okay, so that's what we're doing here. I'm writing so that the sum of these two things, which would cancel that, here, the sum of the two is just phi b. The difference here, I'm sorry, phi b is this thing here. It's the difference between theta and phi with an extra 90 degrees tacked on there. So the difference between theta and phi is this right here, okay? And subtract from that a 90 degree angle, and subtract from that this angle right here. Okay, so that's phi b. Okay, phi b is just the difference between them, but also subtracting pi over 2, and then that lets us write these two equations fairly easily. Theta b is just theta plus a 90 degrees. Okay, here that's what that's expressing. Here's theta, okay, plus 90 degrees is theta b. So that's this equation. Okay, is that geometry all square with you? So I should point out as we go along, this is the cover figure for the textbook, right? So if you have to just look it up, you don't have to, just look at the front of the book. Anyway, what we want are the partial derivatives of these objects. Partial derivative of theta b with respect to phi b. Okay. Well, that's pretty easy. That's a 1. Okay. And partial derivative of theta b with respect to phi. That's easy. That's a 0. There's no phi there. And so this is probably the world's easiest Jacobian to work out. Phi b here, right? Partial derivative with respect gives me a -1 from that guy, and then with respect to phi there, it gives me just a +1. Okay. And these are partials, remember. All right. So this is our transformation for the velocities. Now, what we're mean by a lemma 1 definition here, this is back on page 13 of lecture 9 when we first encountered Lagrange's tricks, his trickery. Okay, it was based on a lemma 1, in which a partial derivative made out of velocities, of a Jacobian made out of velocities, has to be equal to the Jacobian made out of curvatures. And then we just used this a little while ago, 2 lectures ago, on page 60. So that and some other things are what are going on here. This is an example that's often called a contact transformation because it's messing with both the velocity and the momenta, and therefore it's possible to do a geometry that shows this as the kind of contact transformation that we know about. But that's another thing that I find about virtually all of the advanced mechanics books, and that is when they say contact transformation, they never tell you what's contacting what. It's just a name. Kind of like canonical, that's another one. That goes way back to the church, right? The Catholic Church, right? The laws, the canons of the church, right? And so if it's canonical, it's got to be right. Or you're going to go to the Inquisition, right? And no one expects the Spanish Inquisition. Anyway, all of that stuff is ancient history, but it is interesting to do. So what we have to do is be really careful with momentum. That is, the Poincare invariance of this is crucial. That is, momentum and velocity product, the product of velocity and momentum action, if you will, the action sum that goes into Poincaré's relation, or Legendre's transformation, had better be the same, that is, equal with these new values for the momentum and the coordinates that we've just we've set up the coordinate definition. Now we have to set up the momentum definition to go with it. The simplest way to do that is really just to do a transpose inverse of this equation, whose determinant is 1, so it doesn't get very complicated. All you do here is switch the 1 with the 1. It does nothing, but then you do switch these two right here, and so that gives you an equation that is the inverse for this. So here is the transpose inverse. So that's what gives us a transformation for the beam relative momenta to the lab-based momentum. Okay. Now the real reason for doing all this is I'm looking for ways to get a angular momentum out of this for the projectile that is, well, if there's no gravity, constant. That's what I'm looking for, is the possibility of that thing being a constant of the motion. Okay, check that this guy right here and its supposed transpose inverse gives you back this very crucial invariant. Okay, so the momentum transform now, we're going to be writing our old P theta and P phi in terms of these beam relative momenta in that way. So that's what's going into this thing. So here's the original Hamiltonian here, and we have to do a little bit of algebra in order to stick that together into a thing that involves the beam quantities. And while we're at it, we're also going to use the coordinate transformation like that. Had an extra 90 degrees attached to theta minus phi. So I end up with a sign here, and a change of sign in the process, since it was a minus pi over 2, not a plus pi over 2. And let's see if there's anything else I could say that breaks that. Anyway, the same thing happens in the denominator here. Okay, we get a cosine squared from a sine squared. All right, so that's our new Hamiltonian we're going to be playing with in some detail here. This is something just to show the details of making those connections there. And then we've got the gravity, but we're going to do the physics without the gravity. Now, what's the motivation for that? Do you remember how we ignored gravity on the very first day of this class, and quite a few days after that, with respect to the superball, simply by saying that the forces that we're worried about in the boom boom, the double bang, right, are huge compared to the gravity. So gravity only gets to do a little tiny bit which we can ignore during the collision. We're going to pull the same stunt here. Okay, that's some, cheating. Whenever you get a new paper to look at, the first thing you want to do is look at where does the author start cheating, right? Once you've got that down, then things, go up to the point where you call up the author and say, why did you cheat there? Or you say, yeah, it works. Now let's try not cheating and see what happens, and so forth. I mean, this is kind of the way science goes. Okay, so now we're getting rid of our gravity terms, and we're just playing with the Hamiltonian here and looking for things that were constant. And we know darn well that this is going to be a constant, this beam momentum P dot B theta. This momentum is associated with this coordinate. And the reason for that is the partial derivative of h with respect to that is an absolute zero. We've gotten rid of, after getting rid of this, there's nothing left in there to change that. There were lots of ordinary thetas, but the theta sub b is not there. So we have a momentum that we can look at here that is constant. And then, of course, we don't have any explicit time dependence in either of these cases, the original and the Chidi one. So always Hamiltonian, a constant. So we got two constants that we can do. This one right here, and then this guy right here and here. So it's just a matter of sorting them out and really solving for the Hamiltonian in terms of a constant of motion, this lambda here. So I'm going to go ahead and write the lambda in for that. And then we have to take the algebraic part of this that's complicated here. So I'm putting the denominator here now in front of the energy and sifting through this thing to get a quadratic equation in the throwing momentum. And that's the thing that's going to not be constant. That's going to start perhaps 0 or near 0 and be sent to as high a value as we can get if we're trying to optimize this as a war machine or a distance record-setting pumpkin throw. In any case, by moving terms around, which are indicated here, we get a new equation that's almost in the form we want. There's the quadratic term. We have a linear term here. Okay, these things are all just involving the coordinates, as is this, but it's multiplying the quadratic term. And then here is something that's linear, you see, in that momentum. So it has to be brought out and put in the place that is right here. And I bring all this quadratic stuff back here. So now I really have a quadratic equation involving this. And the idea is, at this point, I could just use the quadratic equation and solve for the momentum. It would be a horrendous mess, a bunch of terms. And I've thought about giving problems of doing that. I probably am not that cruel, so I won't be doing that. But anyway, this is the guy that we'd like to solve, and we'll solve it in a way that is more transparent than with all of the terms here. For one thing, let's make the radius of the this r, little r here, little r sub beam, let's make that exactly equal to this. Okay, in fact, most of the time you look in the history books, and this is just a teeny bit shorter, or the one that we showed here, this was longer than the r. But let's just make them equal for this discussion. So that's one of the things that's going to happen. That will make the ratios of r over L go away. Okay, so here's kind of what we're doing. This is an expression here with the minus b plus or minus the square root of b squared minus 4ac is all of this stuff, divided by 2 times the a coefficient. That's the a coefficient right there. And we have also done something else here. This j here is a funny kind of inertia. It's actually a ratio of inertias of the big beam r squared plus the little m, if the little m were sitting right there at the end of the r, okay, and then divided by the factor that would describe the inertia associated with the lever that does the throwing. So that's kind of an interesting ratio that we'll play with. Now that we've made r equal to L, it's a little bit simpler. And then this I here is just the sum of the inertia associated with putting this mass right here and having this one the way it is. Okay, so the J shows up here, here, and then the I shows up right here in the energy expression. Okay. So solving that, plotting it and all that is something that we could do, but we want a little bit more than that. We'd like to get something where we get some actual numbers out of it easily. So at this point, I go ahead and rewrite the whole thing. We've got the p theta and the p phi here. Very easy to go ahead and take that that kinetic energy term. That's all we have. We don't have a potential here. So Lagrangian and Hamiltonian are really the same. And we just transform it to being relative coordinates. In other words, I'm avoiding all the stuff we did on the previous page here. We're just coming at this thing directly, doing the simplification right at this point. Okay, how does that work? Here, the 1/2 comes over to give me 2 kinetic energy. That's what I've got. And that's going to be a constant. Okay, that energy there is going to be a constant. And then this thing, the p theta, that's going to be a constant. And it's consistent of 2 terms. The angular momentum associated with the turning of the theta angle and the angular momentum that's associated with throwing the thing. Okay. Now, put in the beam relative thing, otherwise I wouldn't be able to pull that off. Okay, so what we'll do, and as I said, easier algebra for r equal L, so we'll be getting rid of a couple of things here. That'll be an r squared, and that'll be an L squared, summing that comes together with that one right there. So here's your kinetic energy times 2, and your total angular momentum associated with this, the motion of the beam. That's proportional to a sum of the 2 angular velocities, but it's got this crazy thing in there as well. Okay, now what we're going to do is evaluate these things at a starting point tucked in. Now this is a little bit different from the starting point that we showed with this trebuchet that comes from Arbor Scientific. They have the big mass way up in the air and the projectile down on something that gets dragged. Remember the car that was being thrown, the car was down there so that it could roll for a while and then get thrown, right? So that's not the trebuchet we're talking about. We're talking about a trebuchet that's really Optimum. We're talking about the Siege of Kenilworth trebuchet that was shown on NOVA. I'll mention that later on here. But anyway, we'll start at a starting point I'll call a 9 o'clock. We're going to use that terminology for this model and from one that comes later. 9 o'clock, just on a clock. I'm thinking of a clock relative to the beam. Okay, so I'm leaving the beam in the same place. We're riding on the beam. And we start with this at 9 o'clock, okay? Come down to 6 o'clock. And this is the region where you're getting the energy put into the thing. And then the rest of this is kind of steering as you let this thing fly. And of course the beam is turning at some rate, which we're assuming is taken care of by the constant of that new beam angle coordinate. So this will be 3 o'clock. It's just, 9, 6, and 3 on a clock. Okay? Does that make sense? So we use the terminology. We're at 9 o'clock now. We're at 6 o'clock. We're at 3 o'clock. Or something in between. All right? So there are the expressions that we need to write. And let's look here, first of all, at phi b nearly equal to minus 90 degrees. That's the 9 o'clock position. And stuff that value into this equation here. So whatever the velocity is at this particular point, minus pi over 2, that's what we're talking about here. Let's see if that just goes to 0, and I'm left with an expression that just involves that. Kinetic energy is mr squared. And we're assigning a value of omega to both of these velocities at first. Okay? And then here is that lambda thing that's also supposed to be constant. It just comes out to be, we use this mr squared omega. All right? So that's what we start with. And then we put a lot of energy into the projectile by going to 6 o'clock. Okay. So this is theta b with a 0 on it. That turns this equation here into this. We've got this theta b. So sine theta b equal to 0. So see if there's anything I can say more about that. This sign right here goes to 0, so I'm getting the sum, the squares of them. And this sign right here goes to 0, so I'm just getting mr squared, the sum without the squares there. And then we still have this sign in both of those equations. Just this one has a square on the velocity switch, it's not. So far so good. And then now we assume that this great big beam may have been slowed a little bit. We'll figure out how much that is while we're figuring out what the throwing arm has given us. This is now the release point, okay, the optimum release point, where we've given it as much energy, just thinking that it goes any further here, it's going to take energy out of the projectile. So something had better be available to release it at this point. On the trebuchet that comes from the Arbor Scientific, they've just put a little notch here that's carrying a loop, and just at this point, presumably there's lots of centrifugal force and that thing will just be pulled off at that point. So that is the release point by default for this little guy right here. You see the little notch at the top. For my trebuchets, I just throw the string, so it's simply already got a loop going down in a little notch here, and out it comes to be released at 3 o'clock. Okay, so this gives us expressions for well, we're really interested in what the momentum here is, but we're also interested in theta dot here. How much has that grown? Okay, so the rest of this is just algebra. There's a summary of the three equations that we've taken, and we're asking what are the values at the end here. Okay, so I rewrite this just a little bit. This is with the this expression here, omega squared mr squared, and this is omega. So we're talking about an angular velocity omega associated with that beam mode, and the two equations, one quadratic and one linear, come out of that, and I'm going to divide those two so that I get rid of one power here. So this cancels that, okay, and then have an mr squared here, so I get rid of that. These two disappear, except for the factor of 2, so we end up with a 2 in the numerator. This is a fraction line, okay? And what we have here is x squared minus y squared, that's x plus y, x minus y. We've got an x minus y down here, that cancels. I'm left with x plus y right here, okay? So it gets very simple, at least as far as those variables go. But then we have to worry about the angular velocities and another equation that we also have. So we've got to stick that back into this one to really get an expression here for this, the angular, what the beam's doing. Okay, we're interested in how much energy we've taken out of the beam, as well as how much we've put in of the trajectory. Presumably those will be equal, and so we'll get a certain velocity associated with the beam. So here we have, I think, theta dot is omega, okay? So we have that expression there for theta dot at the pi over 2 place. That's at 3 o'clock, where things are going to be let go. So that gives us a theta dot at 3 o'clock that is this interesting ratio here. So now we're dealing with, deciding how big is the trebuchet throwing arm going to be, not the L, that's going to be equal to the r, and then the driving arm, the little r, little in distance r, associated with this distance right here. Okay, that's the thing that's written with the big R, and it should be the other way around because this is very small. But that's really a ratio with a factor of 4 of the factor for inertia associated with the thrower and the driver, the one that gravity is working on. Okay, so what we'll do is first start out with the case where m is really a lot bigger than we're going to throw a little tiny mass and see what's the best we can do with that. And what we get here is 3 times the angular velocity of the beam. And we're also not, you know, if m is really bigger than m, it's not going to slow very much at all. So it's going to be the same as it started at omega. Okay, but we're going to get 3 times that angular velocity of the projectile. Does this ring a bell at all? That 3 in the Super Ball, the first thing we did lecture 2. Okay.
3 times.
When you considered a really small projectile relative to a big driver, right? That's interesting, right? Because this is simple stuff, right? Let's just remind people, for those that are viewing it on the thing, we are now talking about this point right here for various ratios. That is an infinite ratio that is straight up, or practically straight up. We get a final velocity of 3, right? Now the other case I want to take is the one that throws the most. I'd like to take all of the energy out of the beam. So what do we get over here for that? Okay, let's come back and look at that case next. Okay. This is the optimum case. As it turns out, if I do this, you say I make 4mr squared equal to mr squared. Okay, I get rid of this velocity, and it kills it, right? Okay, and what do you get now for the projectile? 2 instead of 3. Back to here, right? This is 3. Our case that we had with that mass ratio of 3 to 1, remember? We've taken all of the energy out of the big ball, right? And it's all going in the projectile. Now it's down by 50% as far as velocity goes, but in terms of energy, because it's a much heavier projectile, it's a gain, right? You're throwing a lot more. Okay? So I thought that was amusing, and I still haven't been able to take those equations apart in a decent way. If you can do that, I'd really appreciate it, because I'd like to shorten this lecture to 5 minutes instead of whatever we spent. We spent 10 minutes short of an hour doing this, right? I think it could be done in 5 minutes, but there's the thing we're talking about as far as that system goes, the thrower system. Okay, but we've got enough time to take it apart another way and also make connection with other things that happen here. And I'm going to go ahead and speed this through and get us to the point where this one is available. And maybe discuss a little bit of the history of this. This is the Siege of Kenilworth trebuchet. This is a picture of it in, actually this is a picture of the typical unoptimized trebuchet, just the one that is a favorite. Mainly it's a favorite because if I leave it running, in other words, don't release the ball, the projectile, I don't release the projectile, it follows a quasi-periodic trajectory, okay? And probably wouldn't hurt, go ahead and run that just one more time so you can see the difference between that trajectory. It went through the thing out there with 93 miles per hour, if that's the units that we're using here. I believe it is. But then, forever and ever, it follows those trajectory lines. It makes a couple of 3 loops, and then just redoes perfectly those 3 loops. So that's an interesting thing in itself, because it's not typical. This is a wholly nonlinear device. Okay. What's more likely is the one that comes with the siege of Kenilworth. Now, by the way, if you put the numbers from the equations that we just derived into that, it comes pretty close to what they used for the reenactment of the siege of Kenilworth. They spent a whole summer building a trebuchet, reading the literature on what was done, because this was in 1215, and sort of the end of the era for the trajectories. Cannons were starting to come online. Now, cannons were not nice at first. I mean, never are nice, but they were particularly unnice to the people using them, because the metallurgy hadn't gotten very well developed. They were basically using some bronze, and it was lousy bronze. So you'd do a couple of shots, and then the damn thing would blow up and kill all the artillerymen. So, you know, there were people reluctant to use cannons, and this particular case was one of them. But the problem with the Kenilworth one was how to get a really huge mass. Okay? And the freedom of religion was not respected at this point. They went around to all the churches, and all the churches had lead roofs. They stripped the lead off and made the mass. That's apparently what happened in 1215. Now in 1999, or maybe it was 2005, reenactment, I've got that down somewhere. When they reenact, of course the churches didn't have lead roofs, but they couldn't have them anyway. They just simply went and bought huge hunks of iron and stuff to make what they gathered to be the best trebuchet that they got. And then they finally got the thing to work. It took a long time, and then they started shooting it at a leftover remnant of the Kenilworth castle, and actually punctured it. So they proved that, in fact, it was possible to use this device in such a way. So this particular throw is a lot more than 90 miles an hour. A range of 464 feet, so it's over 100 yards. And we're talking about 144 miles an hour on this particular calculation. We're also talking about a motion which is totally chaotic, but very beautiful. And you can see the things that we're looking for every once in a while. That was a good example right there, where it got a pretty good acceleration for the end piece. Now, if you go on the web and just Google double pendulum, there's a high school student that has a double pendulum. Now, it's not like this one. It's just a lever hanging with another lever on it. At the end of the lever, he puts a little blue light that will make the screen behind it glow, so that he can actually draw curves like this. You ought to take a look at that. It's kind of neat. And he's getting chaotic motion like this. The difference between his chaotic motion, of course, is that he doesn't have this weight. He just has the weight of this bar and then this bar, and that's it. And then the lights at the end of the red throwing arm there. So his thing covers the whole screen. This one avoids area down here, but still the basic idea of it going sometimes very delicately. There are moments when it's not really accelerating the thing very much. That's a little bit of an acceleration. Then there's a more acceleration there. Now he's got it really going, you see. But then he says, heck with it. Let's try again. And it's a while before we get a really good throw. Now the question is, what is happening in a really good throw? There was one that's just the opposite. The energy was being given back to the projectile, okay, or from the projectile to the bar. See, that's kind of a dance there, right? There we go. That's a pretty good throw there. But every once in a while I see a really good one. That's also pretty good. That was very good at the end there. Anyway, that's what we're looking for here. Now I'm going to just pause this thing for now and go ahead. Besides the siege of Kenilworth, there's some what may be fake news or false history, but let me get back to our lecture here. And that was, yeah, this is 2005, okay, a NOVA. So you can Google that and get it. It's a whole really interesting summer project that was paid for, but I don't know who. But I'd like to know, because I'd like to get some money like that sometime. Anyway, this one I call Montezuma's Revenge, because there is a claim. Now, this is written somewhere, but the trouble is, people have looked at that and said, I don't think that, I think somebody made that up. And then somebody came back and said, no, they didn't, this really happened. So we're talking about 1500. This is a lot of time since 1215. But they're in South America. And once again, it's the people from Europe making hell for the people in the Americas. And Montezuma was holed up in the castle he had because the Spanish were trying to steal their gold, as that's you know, what they do for a living. So this I call Montezuma's Ransom for reasons that you'll see in a minute. But anyway, I'm showing you here a trebuchet shot that went quite wrong. Okay, and let's see if I can get it to go on this screen. That's the first shot, okay? You can see that is not a good shot. It threw it quite a distance up, but then it destroyed the trebuchet. That's what the account that was written in the story. I call this Montezuma's Revenge. Okay. That was the end of the trebuchet, for sure. If it happened. The question is, did it happen? That's, you know, that's what it is. The history of things like that are hard to trace, even by the most skillful historians. Okay, so let's come back here and proceed. That's the thing that you find in your notes if you look at it. I want to come again and remind us that all of the trebuchet motions that were beneficial as opposed to warlike, all of those motions to build things, not to destroy them, are trebuchet motions of the human body. That is, you really, to do them, have to get a great deal of kinetic energy into the end of either a pickaxe, a plain old wood axe, you're in here, okay? Well, if you're throwing and slinging, of course, you're trying to get energy in it, but this is the one you really had to do. There were no harvesting machines. You had to harvest with a scythe. If you've ever swung a scythe, it's really an interesting thing, and you're going to hurt yourself swinging something. It's very heavy, a very big, sharp blade, but it cuts a whole bunch of wheat in one sweep, and then you take a step forward and do it again. And you do that trillions of times, I would guess, in order to bring our culture to where we are now. Okay? And I don't know how many millions or billions of times we hammered, dug, split. In this country had to get rid of the trees, so they did in Britain. They completely denuded the British Isles with this. That's a whole other story, but they were building things. It just didn't, you know, it was a good way to do it. But anyway, humans cannot stop doing this. I know the feeling because I love this game. I haven't tried this one. I'm afraid of it because it is really addictive, they say. Baseball, also interesting, but much more difficult because we're talking about a much smaller thing at the end of the lever. This one has a lot more room for error. And then while we're at it, we don't do any planetary science without a slingshot, right? You got to go by another planet, get its velocity through its gravity, and then you can go out and see Jupiter and Pluto and all of that, right? So I point that out right now. And don't forget water skiing. That's fun to do. Anyway, here's the deal. What I like to do is make an analogy between the trebuchet and swinging, let's say, a tennis racket. Okay? And the idea is that the trebuchet has a huge force being applied
as it opens up. And the velocity is whatever the sum of the rotation here and the rotation here gives, say that. At this point, the velocity and the force are more or less in the same direction. So F dot V is large, and that's the power going in to this thing. Okay? Later on, okay, V and F are going to be nearly perpendicular, certainly when we get to exactly the 6 o'clock position. Then if it goes much past that, you're actually going to subtract a little bit. But you can keep this going as long as you keep your velocity so it has some component on the force, not on the negative force. So this is mostly to steer. This is to get the energy in. So the message is get your energy in early and then let it flow as you hit the ball. Maybe add a little bit on that end of the thing, the 6 to 3 o'clock part. But the steer or guidance is now easier to do because you're not forcing the thing. You're just letting it flow. Okay? And that's what makes a good golf swing, baseball swing, or a tennis drive. And the serve is the same way. So I'm going to compare two things here, two devices. One's the trebuchet. And the best way I could make a trebuchet would be to take, you know, an old pool cue and put a hook, a half hook in it, a string, and just wing with that. That's hard to do, actually. I've almost killed myself, well, not killed myself, but made great pain with, you know, this thing. Now, my sons were skateboarders, so this came very easy. You get an old pool stick and you get an old skateboard wheel, and you slide it on there. It already has graphite on it. But you slide it on here so it just sticks at some point in the middle of that, and you fling it. Okay? This is the flinger, and it's just the opposite of the trebuchet. Because early on, there isn't as much energy going into this thing. It all comes at the very last minute as the thing slides off or out of this. So the flinger itself, easy to operate, is fairly ineffective. And I'm going to have to go back here to the controls and do show flinger and let that guy go to whatever it does. So start, let's see if I can get this, or resume. Okay, let's reset the timing.
There's a button.
There we go. Okay, so what you can see that you get, you know, say 60 miles an hour. And this is roughly the same dimension as the trebuchet. It's not an impressive device relative to the trebuchet. Well, we've got to analyze that a little bit better. I'm just speaking fairly generally and without anything backing it up. But let me pause this and go back here to an imaginary device that would let us really compare the trebuchet with this thing, okay, this flinger here. Now, as I said, this one's hard to operate. This takes skill. This doesn't. You just line up and wing it, okay? No skill to that. And it goes pretty far because we're talking about really tiny mass compared to your whole body and the stick, the pool cue. So here's what we're going to do. We're now going to imagine that I just have a rotating turntable whose velocity doesn't change at all. It's just going to have omega the whole time. And that means I can write a dynamic potential for that. I can put as my potential the omega squared, which will be constant, r squared, r0 squared, wherever, whatever you're talking about, as far as this thing being thrown. Okay, and the idea is you're going to start out pretty close to the top of this potential, and you're going to fall and gain speed according to what you would do if you fell through a parabolic potential. Okay, and it is parabolic because that's an expression for the energy. So that's what we're doing. We're expressing the potential starting minus the potential at the finish if that's a positive number, and the finish is very negative, so subtracting it is where you're getting your oomph out of that. That's going to work for both of these devices. The one here, which has an axis, you see, and has a, in this case, an L that is, well, larger than the R. Okay, so this is really kind of a weird trebuchet that has a really big L, and just this beam radius here is not as big as L. But the same deal is we're going to look at it starting from 6 o'clock and throwing it. And that's kind of like tennis. You usually don't try to come all the way back. You just come to 6 o'clock and make a drive. They're more accurate. You're playing with more distance over here, so you have more uncertainty, but you get more energy if you start here. Okay? So this one's going to be starting, if it's at 9 o'clock, with that much radius, okay, which will be, say, like this one. Whereas if I start at 6 o'clock, if I do an initial 6 o'clock, well then I'm further down here, so I don't get as much gain in energy. We're going to work that out. That's all very easy to work out. This is just simple software physics. Now, no Lagrangians needed. Okay? And that's always what you want to do in physics. You want to look at the simplest possible formalism, if you will, for a model, simplest possible model. So, here's the Trebuchet's equations of motion, okay? The final here, RB plus L, there's RB plus L, that's where we're going to release the thing at 3 o'clock, okay? And we're going to start with this, and I'm sorry, this is the final, and we're subtracting the initial here, RB squared plus L squared. This, the actual radius squared is, by hypotenuse, R squared plus L squared. So that's your initial, and then when it gets out to the end here, okay, we've got R plus L squared. Okay, so that's what we're looking at as we look at how big is the potential energy on this imaginary roller coaster that has an upside down parabola. This one, much simpler here, we're starting out at RB squared. We're going to let the thing go in there to RB. Eventually we're going to let this one go in there to be RB as well. It means we have to take it all the way back here to 9 o'clock to do that, but we're going to start off just giving it a disadvantage compared to this one, which always starts at RB and goes to the final. Okay, so there's your initial, which gets subtracted from what you're going to have at the final, and what you're having at the final here is pretty much the same, well, exactly the same as what you're getting for the trebuchet. So it's these two against each other. Okay, in our preparations here. So again, final at 3 o'clock, final at 3 o'clock, initial at 6 o'clock, initial here at basically 3 o'clock. I mean, it doesn't have a clock because it doesn't have a winger, all right? It just starts there. Whereas this one starts here at 6 o'clock, okay? And the numbers for that are, well, they're here. And in fact, here's the fully cocked 9 o'clock one. But the half-cocked 6 o'clock one are these numbers right here. And even by just doing a 6 o'clock, which is what you're supposed to do if you're just doing, you know, hitting drives accurate, precisely, is more than this one. Okay, but this really beats it. So I thought that was interesting to see that. Now, there's a couple of things that are also against the trebuchet. When the trebuchet releases this thing, it releases it like that. The thing just comes out of this, but it already has an angular velocity, so you add that. In the lamp frame, that's the final velocity. In this case, you don't take the sum of the square root of the two velocities, you just add them. So the trebuchet has this advantage, and that's why it's winning even at 6 o'clock, but then it really wins at the 9 o'clock. Okay? So that's, you know, what this model finally leaves us with. Okay? There's another meta lesson here about this, all this stuff we're doing, all your physics. Not just, this is not just mechanics, but it sure is in mechanics, true from very long ago. Instead of being a binary or bipolar experimentalists, you know, those grungy guys down in the labs, right? That's the way the theorists think. The theorists think they're up on top, right? Okay? Yeah. It's kind of turned over. Experimentalists are definitely on top now. Okay? Why is that? Because it's no longer bipolar. It's trigonal. Okay? As a theorist, I still have a theorist on top here. Okay? But this is symmetry. You can move triangle anywhere, right? Okay? But you've got not just a laboratory, guys, okay? They're probably doing some theory themselves. Okay? Because we've got these guys, right? Well, it's electronics. That's a big help. And maybe one of the days we're going to have some quantum electronics to go with that. So that's really what it is. Now, as I said, our mechanics has a U.S. approach. It's Newton's laws and Cartesian coordinates. Most people, that's in this department, I would say that's 90% of people just know that. Then we have the French trio, Lagrange equations, okay, and generalized coordinates. That's the four-wheel drive guy that we've been touting. It works just about anywhere. Or the German approach, and this is what we're going to learn next. Christoffel coefficients, okay, that determine the differential geometry. But today we started out learning, for the trebuchet anyway, what the Irish approach is, as I say, powerfully created. This is pride and precision of the Germans. This is the elegance of the French. Okay, and then there's the art of approximation, which is really what physics is about. Physics lives and dies by the models and analogs that it makes, however terrible they are sometimes, or however beautiful they are some other times. Now think about it. Without this, would we have had a success just recently with respect to gravitational radiation? We really relied on the numerical solutions of the black hole models. And if you look at them, they're pretty cheesy models, but they're the best we can do right now. We can still probably do better. And maybe even we can make some actual theoretical things that you can sort of hand wave your way through at least. That hasn't happened yet. But boy, this was important. This was really important to get something that sort of fit. It fit pretty well. That little boop. It sounds like what you hear when you left your faucet dripping, right? Boop. Boop. Only this boop involved, for a brief second or two, the same amount of energy coming out as all the other stars that we can see now putting out at once. Whoops, that's a lot of energy. I mean, I thought supernova with 10 times the energy our sun will put out in its lifetime. Okay, a supernova does that. But all the suns at once, everywhere, that's what you had emitted from that. Whoop. With that, we'll stop and we'll take on some of this German approach in the next lecture. You have no homework now. We will give the next homework on Tuesday, but it'll be German homework. So get ready.
It should be what?
Okay.